So in this lecture we are talking about the high dimension space. The high dimensional data has become very important, and the high dimension space is very different from a 2 dimension and the 3 dimension that we are familiar with. For example, if I can talk that generate n points randomly in the d-dimensional space where each coordinate has mean 0 and unit variance, and for sufficiently large d, there is a high probability that the distance between all pair of points will be same. This is one of the example, and we are discussing these things in detail in this unit. Also, the volume of unit ball in d-dimensional space, the set of all points x. So when you can say a unit ball, that means the set of all points in that space, I can say it is Rd. That is the d-dimensional space, such that mode of x bar, if this is a vector, it is an Rd, is less than or equal to 1. It goes to 0. So what is means the volume of d-dimensional sphere with unit ball. Unit ball means its radius will be 1. It goes to 0. As your d is tending to infinity. So this is the first results that we are discussing later on when we build up some of the quantity in these high dimensional spaces. The volume of high dimensional space of unit ball is concentrated near its surface and also centered at its equator. That means all the volume of a d-dimensional space is centered or concentrated near its surface. So if you consider a d-dimensional unit sphere, so all the volume of this unit sphere is centered at its surface, nearby its surface. Also, there is an equator is there, and nearby equator also you can find it's all the concentrated thing. And these are the important property which we need to discuss in this high dimensional spaces. For that, I required some certain things which you probably have studied in your statistic course. In that, the first one that I want to discuss here is the a law of large number. So discuss this law of large number. First of all, I should know that one-dimensional Gaussian with mean 0 and unit variance, that means mu equal to 0 and sigma is 1. Mu is 0, that means mean 0 and variance, unit variance is sigma. Then what will be the distribution of this? You should know this. So what I'm asking you is one-dimensional Gaussian with 0 mean and unit variance. What will be this? It's generally denoted by n.
Standard normal.
Yeah, it is mu sigma square. Right? So here it is mean is 0, so it is n 0 1. Sigma is 1. So what will be this? 1 by square root of 2 pi
2 pi
exponential of, that is e power, or you can write exponential of minus x square upon
square upon 2.
2. Okay, in general, if you want to write down the normal distribution for this, that is nx mu sigma square, that will be 1 upon square root of 2 pi sigma square exponential of minus of x minus mu square upon 2 sigma square. So this is the one dimensional Gaussian with mu, that is mean mu and variance is sigma square. So if we generate a random points in d-dimensional space, when I talk a d-dimensional space, you should know what you mean by this RD. That is a cross product of R, d times. And in that manner, this is x1, x2 up to xd. This is a vector in d dimension, where each of this xi is belongs to R for every I running from 1 to d. So that is the d-dimensional space. For example, you have R2, then you are presenting this R2 by two-dimensional space. Then you have R3, that you have three-dimensional space, x-axis, y-axis, and z-axis. Likewise, this is RD, so it is a d-dimensional space. Okay, and we need to generate a random points into d-dimensional space using Gaussian to generate its coordinates, the distance between pair of 2 points. So if you have 2 points in this space, how to find out the distance between 2 points? Suppose in R2, so you have 2 points here. If I want to calculate the distance between these 2 points, let's say this point is x1, y1, and this point is b, x2, y2. And if I want to calculate the distance between these two, then how I can calculate? Yes, I need answer from you guys.
I think, sir, we have a formula under root y2 minus y1 whole square plus x2 minus x1 whole square, I think.
x1 minus x2 square
Yes, sir.
plus y1 minus y2 square. This is the distance between these 2 points. If it is in 2 points in R3, it is given. Let's say this is the point A, which is x1, y1, z1, and this will be x2, y2, z2. Then how to calculate the distance between these 2 points? That is again AB will be square root of x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. In that manner, if you have 2 points in, let's say, y bar, which is in RD, d-dimensional space, z bar, which is also in d-dimensional space, both of them are in RD, then the distance between 2 points, the distance between y bar and z bar is denoted as mode of y bar minus z bar. So that is the square root. So if I don't want to write down the square root, I will take a square both sides. So it is y bar minus z bar square. It is y1 minus z1 square plus y2 minus z2 square up to so on yd minus zd square. If you don't want to write down the square, you just write down y bar minus z bar under root of, And if I can write down whole this thing in the summation notation, summation I running from 1 to d, yi minus zi square. So is the sum of, this is the sum of d independent random variables. So this yi minus zi squared is a random variable. Okay. So the distance between this to y bar minus z bar is the sum of d independent variable, and the distance between pair of point is essentially same in d when d is a large, that we are trying to see. If one average the n independent sample of the random variable x of bounded variance, the result will be close to the expected value of the x. In the above summation that we have here, there are d samples where each sample is a square distance in a coordinate between 2 points of y bar and z bar. Here we have give the general bound called the law of large number. And specifically the law of large number is stated as this way. That is the probability of modulus of the average value x1 plus x2 plus xn upon n minus expected value. The bound between the average value and expected value greater than or equal to epsilon is less than or equal to variance of x upon n epsilon square. We'll prove this one later on. The large number of the variance is random variable, and the greater probability that the error will be exceeded by epsilon square. So what is this? What does it mean of x minus a less than epsilon? It means that your x is between. So this means that epsilon is less than x minus a less than epsilon, and so your a minus epsilon x is less than epsilon, a plus epsilon. So this is the bound you will have. So here is exactly outside this. That means epsilon is here. This expected value is here, and this is the mean. This will be the mean minus. So I say this is mean is, I'm just denoting as mu minus epsilon and mu plus epsilon. So outside this, that means all this value which are outside, it has bounded by this value. That is variance of x upon n into epsilon square. And if your n is large, that means you pick up a large number of samples, then this, that means nothing will come up on this side. So that is the meaning of this law of large number. So similarly, if the epsilon is large, then this probability is smaller. Difference will be exceeded epsilon, and hence the epsilon is in denominator here. And notice that the epsilon square makes the fraction dimensionally very less quantity. If the epsilon is large, its square will be very large. So in that manner, this will be very small quantity that we have. That means the chances that here and here nothing will come up is goes to zero kind of thing which we have. So we'll use this two inequality to prove the law of large number. We need a two inequality to prove this one. We'll prove this one later on. The first one is a Markovs inequality, which states that the probability that the non-negative random variables exceeded a bound by expected value of the variance divided by a. The another, and that Markovs inequality, let me prove first that one, and then we'll go for the another inequality. and then we'll go for the law of large number. So this is the theorem that I'm making, that is called Markovs inequality. So what is that state? Let X be a non-negative random variable. Then for a greater than 0, probability of X greater than or equal to A is less than or equal to expected value of X upon A. Let me do the proof of this. So for continuous random variable, X with the probability P, density is P. Then what will be the what is the formula for expected value of X? As we know that it is a non-negative, what we have into given is non-negative random variable. So that's why it is integration 0 to x into p dx is there. Now this x will split, this integration I am splitting in two parts, 0 to a, x into px dx plus a to infinitive x into px dx. As this is a random variable and which is a positive, so I'm just, if I remove this one, then this quantity, whole quantity is a bigger than, is a smaller than this quantity. That means a to infinitive x p dx. So what is the things is just we have added this quantity, and this obviously this quantity is positive, so that's why this will be bigger than this. Now here what we have, it is x is greater than or equal to a. That is, we need to calculate the probability of x is greater than or equal to a. So here this x, I'm taking here a to infinity. So in this interval, x is bigger than, all the values are x is bigger than. So that's why I'm just taking out, that is greater than or equal to a to infinity px dx. And what is this? It is actually a into probability of x greater than or equal to a. So that proves that. So therefore, what we have achieved, that exponential of, sorry, this expected value of x is greater than or equal to a into probability of x greater than or equal to a, and that will leads to the our inequality, that is x is greater than or equal to a is less than or equal to expected value of x upon a, and this is known as Markovs inequality for x is non-negative random variable. The same proof works for the discrete random variable. So here what we have did is we have worked with the continuous random variable. Instead of that, if it is work with the discrete random variable, you have a summation sign is here. So summation is running from 0 to x, and then you split that the things, and all the things, instead of integration you will have a summation is there. So nothing is changed for the, so I'll just write as a note, that is the same proof works for discrete random variable. with sum instead of integration. So instead of integrals, you just use the sum. That will gives me a discrete random variable. Now corollary of this result. So prove that the probability of x greater than or equal to b into expected value of ex is less than or equal to 1 upon b. So how we can get this inequality? From the Markovs inequality. So Markovs inequality, as we know that, so if we can try to prove this one, can somebody try to establish this? See what we have a Markovs inequality, just write down and it will gives me this answer. Using Markovs inequality, what we have? Probability of x greater than or equal to a is less than or equal to expected value of x upon a. So instead of a, what we have here? B into expected value of x. So just put a is equal to b into expected value of x. So that will leads to probability of x greater than or equal to b into expected value of x is less than or equal to expected value of x upon b into expected value of x, and that will gives me 1 upon b. So it is straightforward. By just putting the one value of a here, we'll get this. And this Markovs inequality is bound tail of distribution using only the information about the mean. A tighter bound can be obtained by using the variance of the random variable. Okay. So another important result that we'll use to establish the law of large number is the Chebyshev inequality. So let x be a random variable and then prove that for c greater than 0, probability of x minus expected value of x is greater than or equal to c is less than or equal to variance of x upon c square. Now to prove this one, first we note that the probability of x minus expected value of x is greater than or equal to c is same as a probability of x minus expected value of x square greater than or equal to c square. Let us take this value as y. Let y equal to mod of x minus expected value of x whole square. Now this y is a non-negative random variable. Okay. So we note that y is non-negative random variable. Also, what will be the expected value of y? That is expected value of mod of x minus expected value of x square And what will be this? Can you just recognize using the some knowledge of statistics?
Variance.
Yeah,
Variance.
this is a variance of x. So the expected value of y is nothing but the variance of x. So now y is a non-negative random variable. Okay. So using the Markovs inequality, what we can say? So Markovs inequality can be used or applied to giving. We'll start with the probability of mode of x minus, that is our objective, is to establish the mode of x minus expected value of x greater than or equal to c. This is our objective. And that probability is same as this one. So that's why that is equal to, we can write down the probability of mode of x minus expected value of square is greater than or equal to c square. Now using the Markovs inequality, you just see that what is the Markovs inequality? Probability of x greater than or equal to a is less than or equal to expected value of x upon a. So here this is y, as we have talked. We have taken this as y. So if I can say this is equal to probability of y is less than or equal to c square. So if I apply, instead of, now y is a non-negative random variable, so we'll have this is less than or equal to e of y upon c square. But what is e of y? We have discussed e of y is nothing but the variance of x.
Variance of x.
Yeah, so this is variance of x upon c square, and that is exactly which we want to prove. We want to prove that the probability of mode of x minus expected value of x greater than or equal to c is less than or equal to variance of x upon c square, and that we got here. Okay, so that is completion of this Chebyshev inequality. So the law of large number is follows from the Chebyshev inequality together with the fact about the independent random variables that we require. So you just recall some of the results from your statistics, that if you have e of x plus y, then what you can write down about this one, that is e of x
Plus e of y.
plus e of y. The variance of x minus c, that you can write down as variance of x. A variance of x into c, that we can write down as c square variance of x.
Variance of x.
And if your x and y are independent random variables, then e of x into y will be e of x into e of y. And this fact is also implies that if x and y are independent, then variance of x plus y will be variance of x plus variance of y. How we can see this one? That is easy to see. Let me try to give the proof for that. The variance of x is nothing but the e of x plus y square minus e square x plus y. So this is not right. This, it is e of x plus y square minus e of square y x plus y. But x plus y square will be e of x square plus 2xy plus y square minus e square of x plus y. As per this, it is e of x plus e of y whole square. So this is, we can write down e of x square plus e of 2 times xy plus e of y square, as we have used this first quantity. This is expanded, that is e square x plus 2 times e of xy, sorry, e of x into e of y plus e square y. So if you combine this one and this one, so this is of minus, so all this quantities of minus sign. So if you combine this e x square minus e square x, that will give me variance of x. This will give me, this two quantity will give me variance of y. Now what is 2 times? So we already know that e of x into x is e times e of x. So that's why it is 2 times e of x into y. And previously you just see that if x and y are independent, then e of x into y is e of x into e of y. So as per that, this quantity is nothing but the 2 times e of x into e of y, and that is exactly the same quantity we have here. So that's why this is variance of x plus variance of y. So what we have proved here, it is variance of x plus y is equal to variance of x plus variance of y. See, all these things we have discussed if x and y are independent variables. Okay, so that is if x and y are independent. Otherwise, it will not be possible. Now, let us try to prove that we have talked about, that is law of large number. So to prove this one, let x1, x2 up to xn be n independent samples of a random variable x. Then probability of mode of x1 plus x2 plus xn upon n minus expected value of x is greater than or equal to epsilon less than or equal to variance of x upon epsilon square into n. So this is our objective to prove. We'll use the Chebyshev inequality first to do this. So the solution or proof for this by Chebyshev inequality. Let us recall what is Chebyshev inequality here. The probability of mode of x minus expected value of x less than or greater than or equal to c is less than or equal to variance of x upon c square. That is the Chebyshev inequality. So here we have probability of mode of x1 plus x2 plus xn upon n minus expected value of x greater than or equal to epsilon. So instead of c we have epsilon here. Instead of x we have this average value x1 plus x2 plus xn. So that is less than or equal to, I can say, variance of x1 plus x2 plus xn upon n upon c square, that is epsilon square. And as per the previous discussion, that is the variance of x into c. It is a c square variance of x. So that's why here we have a variance of x1 plus x2 plus xn upon n square. So this n square is c. 1 upon n square is a c. So that will gives me that is equal to 1 upon n square epsilon square into variance of x1 plus x2 plus xn. Also with the previous discussion that variance of x plus y is equal to variance of x plus variance of y if x and y are independent. So here we have considered this x1, x2 up to xn are n independent samples. So that's why the variance of x1 plus x2 plus xn will be variance of x1 plus variance of x2 up to so on. So that's why this will gives me that is equal to 1 upon n square epsilon square into variance of x1 plus variance of x2 up to variance of xn. But what is variance of x1 plus variance of x2 plus variance of xn? That is exactly the variance of x. So that's why this is variance of x upon n square, sorry, n square epsilon square. 1 minute. Oh, this is not the things what I'm saying. That is n square epsilon square, and the variance of x1 plus variance of x2 up to variance of xn is actually n into variance of x, because the variance of x1 is same as variance of x, variance of x2 is also same as variance of, because all of them are a random variable from x. So that is n into, so it is n times variance of x, so it is n into variance of x. So that's why it is variance of x upon n into epsilon square, and that is exactly what we need is probability of mode of x1 plus x2 plus xn upon n minus expected value of x greater than or equal to epsilon is less than or equal to variance of x upon n epsilon square. The law of large number is quite general and applying to any random variable of finite variance. Later we will look a tighter contraction, that is the contraction is there, or here we are later on we'll see that what is a tighter contraction bound for the spherical Gaussian and the sum of the 0, 1 value as a random variable. So as an application of law of large number, let us see. Let Z be a d-dimensional random point whose coordinates are each selected from mean 0 and 1 by 2 pi variance Gaussian. We set the variance to 1 upon 2 pi So the Gaussian probability density is equal to 1 at the origin, and it's bounded below through the unit ball by constant distance. So by law of large number, the square distance of z to the origin will be this with the high probability. In particular, there is a vanishing small probability such that the random points z could be lies in the unit ball, and this applies to the integral of probability density over the unit ball must be vanishing small. On the other hand, that means if you can see on the other side, the probability density in the unit ball is bounded below by a constant, and thus the conclude that the unit ball must be vanishing for a small volume. So it is very interesting results actually, that if we go, what will be the volume of a unit ball for higher dimension? As per our discussion or using the law of large number, the volume, if you have volume of a sphere, so you just see that three-dimensional sphere, and if you have in RD dimensional, if your D is becoming large, if you can take that as n to infinity, then according to the law of large number, it says that the volume of this d-dimensional sphere is tending to 0. The volume of this one is tending to 0. Also, there is another things that we can see, and we'll also discuss later on, that if we draw 2 points, so in this unit sphere, if you can draw 2 points, y bar and z bar, from the d-dimensional Gaussian with the unit variance in each direction, then mode of y bar square is approximately d, and mode of z bar square is approximately d. What do you mean by mode of y bar square? The mode of y bar square is actually a distance from the origin. So the modulus of this one, as you have discussed, for example, in R2, you will have it is mode of x bar is the square root of x1 square plus x2 square if x bar is x1, x2. In R3, mode will be square root of x1 square plus x2 square plus x3 square. So in y bar, it is a square root of y1 square, y2 square up to yd square. That is the modulus. So it is approximately d. And the mode of y bar minus z bar is approximately 2d. Because the expected value of yi minus zi for each I square of this one is modulus of yi square plus, so expected value of yi square plus expected value of zi square minus 2 times expected value of yi zi. So as per this is d, this is also d. So this will be gives me d, this is also gives me d. Okay. And so if it is 1, the expected value is 1, then it is this will be d square. So this will be a fixed value. So by Pythagoras theorem, it says that, so what I'm talking about here, that is, this is y bar, here it is 0, this will be z bar. So what is this y bar minus z bar? The y bar minus z bar is this vector. So if you can see in the 3-dimensional, this is my y bar vector, This will be my z bar vector. So to calculate the y bar minus z bar, you have to copy this y bar into the reverse direction here. So y bar minus z bar is this vector actually. And using the Pythagoras theorem, you just see that any two vector, that is y bar and z bar, they are orthogonal. Orthogonal means that means they make a 90-degree angle between them, which also we'll discuss later on in detail here. And that is the last thing that I want to talk here. That is a master bound for the tail theorem, and we'll not discuss the proof for that one. That is a master tail bound theorem. Let x is equal to x1 plus x2 up to xn, where x1, x2 up to xn are mutually independent random variable with zero mean and variance at most sigma square. And let A is bounded by root 2 and sigma square, 0 and root 2 and sigma square. And assume that expected value of x I raised to s is less than or equal to sigma square s factorial for s is equal to 3, 4 up to integer function a square upon 4n sigma square. Then the probability of mode of x is less than or greater than or equal to a is less than or equal to 3 times e power minus a square upon 12 n sigma square. So the proof of this one is given in the book of Blum, Hopskopf and Kanan, Foundation of the Data Science. That is a book name. And the master tail, see, in this series, a tail bound is important. For example, in Markov's condition, the condition is x. So here in general, it is saying for anything. For example, in Markov's condition, the condition is given that is x is greater than or equal to a. And the tail bound that we have, it is a probability of x is greater than or equal to a less than or equal to expected value of x upon a. For Chebyshev inequality, your x is anything. There is no condition on x. Here, x is greater than or equal to a is the condition. Here, there is no condition on x. Then here you have probability of mode of x minus expected value of x greater than or equal to a is less than or equal to variance of x upon a square. Then there are other type of conditions we have, and according to that we have a tail bound for that. For higher moment, you have this probability of, so here you have probability of mode of x is less than or equal to a is less than or equal to x raised to r upon a power r. This is called the Markovs, using the Markovs for higher moment. This is a moment bound. And so on. There are other boundary problems are there, but we'll not discussing all of them here. So I think so this we can stop for today.